Alright everyone, in this video I'm gonna summarize free fall, and I'm gonna post this as a lecture 3 so you can go back and watch anytime you like. Free fall motion is simply 1D motion along vertical, and anybody is in free fall will have a constant acceleration g, and the velocity will be increasing and increasing. Let me actually draw velocity with red maybe. So acceleration is constant throughout and velocity increases as you fall. Gravity simply pulls you down. The last vector should be longer. Let me exaggerate. So velocity increases, ay is equal to g downward. It's negative. We'll take ay as g, negative downward 9.8, and we'll replace all the values of ay with g. This value will be negative, so either we'll replace minus g or take the value as minus 9.8 equivalent. As we fall, we have an air drag upward. For now, we ignore this. For most cases, we will consider air drag is not significant, so it doesn't change the motion, and we will focus on that. But if we drop a feather and a hammer, they won't fall at the same time. So normally for regular objects, I draw a smaller mass and a larger mass from the same height. Let's say this is 4m. They will fall to the ground at the same time. If the height is the same, time is also the same. So height 1 is equal to height 2. Delta T1 will be equal to delta T2. But if we have a very different case like a feather and hammer, or if I have a paper and I'm dropping it with a ball, they will not fall in the same time. Air drag becomes important, and we are ignoring this. And we're looking at cases where they all fall at the same time. We'll go back to air drag when we study forces. This picture is showing an astronaut, David Scott, doing an experiment on the moon, and there is no air. When you drop a feather and a hammer, they will drop at the same time. But if there's an air drag like on Earth, they will not. So he dropped them on the moon during a moon mission, and they dropped at the same time if no air drag. You can watch the video on YouTube. So no air drag on the moon, feather and hammer drops at the same time. Alright. But we will assume we have no air drag. Anyway, so whatever we drop, they will drop at the same time. And the situations we're looking at will be where air resistance is ignorable, like in this case here. What is happening? Down is negative. If you remember, for vertical we call it y, up is positive, down is negative. We'll stick with that. So the motion will be downward if it's falling, like in this figure here. Let me see if I can use a hand. Like in this figure here. And it will keep falling. It will have a zero initial velocity. The book called these Vy, so I'm going to call them Vy. I took these figures elsewhere. Vy initial is 0. It falls down, down, down. When it reaches here, it will have a Vy final. It will be a large velocity. If I draw a velocity versus time graph, it will start at 0, increase downwards. It will become more and more and more negative. Negativity for a vector only shows direction. It means it's downward. And this image here shows the motion diagram. It will have a small velocity downward, larger and larger. If I throw something upward, it is also called free fall. We all know by experience that it will go up a little bit and come back down. If I throw something downward, it is also called free fall. They all will have motion in the gravity. So any motion that is only in the gravitational field, gravitational acceleration, are called free fall. Here I push the ball upward. I give it an initial velocity. Notice here Vy initial is upward. Upward it will be decreasing, decreasing, decreasing. At the top point it will have a zero. I'll call this Vy top, zero velocity. Momentarily stop there and fall back down. The second half of the motion will be exactly the same as this guy here, but the first half is different. One important information about free fall of this sort is that at the same level, velocities will be equal and opposite. So here if I have, let's call this Vy1 upward, Vy2 on the equal level on the other side will be minus Vy1. Downward, the same strength. Or I can say speeds are the same, velocities are inverse in direction. Remember speed as the magnitude of velocity. So that's one important information. I'm going to summarize it here again. Let's say I'm throwing something up from the floor. It will have a Vy initial. It will go up, 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 up. And at some point it will stop, come back down, and as it reaches back to the ground it will have a Vy final, downward. Magnitudes are equal to each other, so I can say absolute value of Vy initial is equal to absolute value of Vy final, or I can say Vy final is equal to minus Vy initial. Equal in strength, opposite in direction. At the top, Vy top is 0, and if I pick any level and look at the velocities there, and I'm going to call this again Vy1, call this dude Vy2. Vy2 will be equal to equal in magnitude and opposite in direction to Vy1, or I can say Vy1 is equal to, well, equal in magnitude and opposite in direction to Vy2. Another important information for this type of motion is that it's a symmetric motion, which is why velocities are the same at same positions. I mean, at the same level, not really same position. Well, we can say same position too. It will come back down along the same line overall. For this case at least. But if it takes delta t1 to go up, it will also take delta t1 to go down. I'm going to call this delta t2 to go down, and the information is that delta t1 is equal to delta t2, same amount of time. Total time, delta t total is equal to either 2 times delta t1 or 2 times delta t2 equivalent, right? Or to a delta t1 plus delta t2. You add all those times. So that's free fall. That's all the properties. It's an accelerated motion. So equations are for uniform acceleration or non-uniform velocity. We have a change in velocity. Vy changes depending on if I throw something up or down. It increases or decreases. And so we have an acceleration. It will be ay, and it's equal to, well, I'll say g, and g is minus. So all these equations we're going to write in terms of free fall. What I'm gonna do, replace Vx by Vy and Ax by Ay, which is we'll replace as minus g because this is what the book does at certain points. So then for free fall, here are my equations. The first one will be Vy final is equal to Vy initial minus g delta t. Notice I replace this by Ay, which is minus g. That's always the case. This equation, I'm gonna use, it's very hard for me to keep color convention, but to make it a little bit less confusing, I'll try to do that. So all the x's will be replaced by y, and ay will be minus g. And when I do that, I'll have this here, y final is equal to y initial plus Vy initial delta t minus 1 over 2 g delta t squared. It's possible to put here ay as plus ay and replace it by minus g, or just put g and say that the g is minus 9.8. All the equivalent approaches, but let's stick with this one. We'll put it as g, and we'll say this is equal to, g is equal to, put it as minus g, and g is equal to 9.8 meters per second squared. So we should include this negativity once, and we are taking magnitude of g to be 9.8, include negativity here once, showing that g is downward, always downward, right? So it's negative. Notice g is an acceleration due to gravity. So acceleration is a vector. It is a vector. Thus, the negativity means the direction. Magnitude is 9.8. Let's do the last equation 2 here. Please write these down for yourself too. This will become, under the new approach, everything will be y, and ay will be minus g. I will have this Vy final squared is equal to Vy initial squared minus 2 g delta y. So these are my equations for free fall. Let me box them all. Here is one. Oops, this box is not gonna work well, but I'm gonna box it still. Here's the other, telling me vertical distance, so I can use this to calculate vertical distance. Here's another one. This one can be used if I know the vertical displacement delta y and initial or final speed. Delta y, initial or final speed, I can find the other one. Or if I only know initial and final speed, I can find delta y. A ball is tossed upward. So we looked at this motion already, right? I'm tossing a ball upward. It will go up, 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 come back down with the same magnitude, opposite in direction, velocity, right? Vy initial, Vy final equals to minus Vy initial. At the top, Vy top is 0. But it says at the ball's, at the very highest point at the top, what is its acceleration? Acceleration is always g here, so ay equals to g. It's downward, negative. When I put this in this format, that means I mean magnitudes, right? All right, so it's negative, downward. An arrow is launched vertically upward. It moves straight up to a maximum height, then falls to the ground. The trajectory of the arrow is noted. Notice here again, if I want to talk about velocities, this guy here upward, Vy1 equals in magnitude to Vy2. Let's remember that. Also remember that the time it takes to go up, oops, let me try that again. So the time it takes to go up, delta T1, is equal to time it takes to come back down, delta T2, and total time, let me put that here, is equal to delta T1 plus delta T2 over 2 delta T1 or 2 delta T2, right? Because they are equal to each other. So find one time up or down, you're done with the total time, because delta T1 is equal to delta T2. All right, at which point of the trajectory is the arrow's acceleration is greatest, the least? Ignore the resistance, the only force is gravity. Acceleration is G, always G. So it's always G, no greatest. Always AY is equal to G, constant. There is no greatest or least acceleration. An arrow is launched vertically upward. It moves straight up to a maximum height, then falls to the ground. The trajectory of the arrow is as noted. Which graph best represents the vertical velocity of the arrow as a function of time? Good question. So I'm going to look at here. I have an upward velocity first, and it's going upward. Velocity is up. Let's think a bit slower here. The acceleration is G and down. Notice the acceleration and velocity, AY, is up, and velocity is Vy, sorry, AY is down. Vy is up. Vy is up, AY is down. Let me retry that. Oops, not that. AY is down, right? It's always G. How can I write that down? All right, mistakes are a part of our lives. AY is down, right? And Vy is up in the first part of the motion. First part of the motion. By that I mean as it is going up, as arrow goes up, right? So it will go up, up, up. At here, at this position, it will stop. It will have a Vy top equals 0, right? We discussed that. So what is happening now? If AY and Vy are in opposite direction, we have slowing down motion. Remember that? So the arrow is slowing down. Slowing down in positive direction. Why positive? Because it's going upward. Up is positive. So in the first part, I'm looking at a graph of, there's an initial velocity, Vy initial, and it gets less and less and less. If I want to draw a motion diagram for the velocity upward, would be something like this. Which graph would give me that? The first one gives me that. I have an initial velocity here. Gets less and less and less, goes towards 0. It will reach 0, right, at the top. Yes, so this would be the top point, Vy top. The rest I don't know, but this guy looks okay. This guy also looks okay. This guy is slowing with a curve. I'm not looking at that. This would be non-constant acceleration. I'm not looking at it. My acceleration is constant. I would have a straight line graph. It should be a straight line. I know that because slope is equal to acceleration, remember? And it should be constant. Just one straight line. Remember, for this guy, acceleration would change because slope would change. Drawing tangent lines, steepness decreases. So this is not correct. This could be right. This is similar to the second one, right? Not correct because AY is not constant. Also, I see velocity increasing. Here, our velocity is decreasing. So I did my first check. Second part. Let me use blue here. What will happen? Now it's coming back down. It will have zero velocity at the top. Turn back down. At the same level, we'll have the same velocities, remember. And hit the ground. So its velocity is increasing now. And it's negative. Whichever graph gives me that. This gives me that still. But I see here a section that it's zero for a while. I have Vy top 0 here, but this is momentarily, just very short time. I need that very short time, so I'm eliminating this guy. I'm also eliminating this guy because velocity turns back, starts increasing here. That's not correct. Only this guy is left, so this is double checked. It's decrease in velocity in the first part of the motion, then it turns back, comes back down, increase in velocity. Let me just put the second part in the second part. So that's good. My answer is D. A heavy rock is dropped from rest. This is another question. Heavy rock is dropped from a cliff, from rest as well. No initial velocity. 100 meters before hitting the ground. So the height here is 100 meters. Okay, 100 meters. So I'm gonna draw a picture, which is already done for me. This is motion diagram. I can imagine that we don't always have to draw a motion diagram, but it helps us understand what happened. If we like, we can draw it. Velocity will increase, increase, increase. A is downward equals to G. Here they said A is equal to minus G, but we know this is minus. So as long as I include the minus, I will be all good. So the height, I'm going to call the distance between the initial and final. That would be delta y. But we often call it height. So I'm going to call it height, 100 meters. How long does the rock take to fall to the ground? And what is its velocity when it hits? So we drop the rock here. Oh, we see the rock here. I was drawing the rock. With a 0 Vy initial, I like putting stuff on the picture. They put all the values here, but I'll put them on the picture. And it will drop to the ground with a final velocity we don't know. So we're asked to find that. Also, how much time passes for the rock to come from here to there, delta t. We don't know that. I'm going to go back and check my equations. First, I have to find delta t. Then I have to find Vy final. I don't have to find them in the order they're asked. In any order I can go. What do I know is this. If I take this position to be 0, Y initial to be 100 meters high, my Y final will be 0. So I know Y initial and Y final. Y initial is equal to 100 meters. Y final is equal to 0 meters. So that's what I know. I know these guys. I know G. magnitude is 9.8 meters per second squared, and it's negative, I'm going to go back and check my equations. Which one I can use? Here is how I converted my equations to free fall. Simply replace x's by y's and a by minus g. I'm going to input, since I included minuses here already, I'm going to input my g as 9.8, not as minus 9.8. Then I'm including g and minus twice. It's not good. So keep that in mind. It's done in either way. They input g as positive here and its value is minus 9.8 sometimes in the book, and sometimes the other way around. So I know this guy and that guy. I know this is 0. I can get the time from here and then use time to get the Vy final. That would work. Or I know delta y because I know y initial, y final. And I know Vy initial 0. I can get Vy final. Then input it in here to solve the problem. So either way will work. Since I have delta t squared here, I don't want to deal with squares, so I'm going to go this way. I'm going to go this way. I'm going to use this equation, Vy final squared is equal to Vy initial squared minus 2g delta y. I know this dude, that dude, and that dude. So I'll say delta y is equal to y final minus y initial. And that will be equal to 0 meters minus 100 meters. So minus 100 meters. This guy is 0. I will say Vy final squared is equal to, oh, there's squared here too. Don't worry, it's fine. Is equal to minus 2. G is 9.8 meters per second squared. Delta y is, this is minus, don't drop that. If we have this mistake here, forget the negativity here. Let me try to erase that. Keep the negative sign if you have them as negative. If we forgot the negativity here, we would have a sign problem. Just take the absolute value. Then most often it's not a big deal. Sometimes it is, though. Be careful. But notice how negativity goes away. And if I am solving the problem right, it should go away. This guy and this guy, minus times minus is plus. So I'm going to have a plus value here. And I'm going to find this Vy final equals, I actually don't have the answer, and I'm going to do it here with you folks. It's 2 times 9.8 times 100 in square root. Let's do that. Let's do that. On my, this is how my computer calculator works. It was 2 times 9.8 times 100. Notice how I dropped negative signs because I know negative times negative is positive. So here is my velocity as it hits the ground. 44.27 meters per second. So now I find this. I'm gonna use red here. And I can use to find delta t using this. Vy final is equal to Vy initial minus g delta t. And I'm going to solve for delta t. I have to do some rearrangements in here. One important thing in here is that we find the magnitude of Vy final, and we know it's downward, so it's negative. When we include this negativity here, we'll input this guy as 9.8, and that Vy final being negative. So this didn't come out of this equation. That's what I want to warn you about here. But logically, we know it's downwards. It's negative. Over here, again, this negativity will be a bit confusing. But you can assume absolute values. This will not give you trouble at this point. So minus 44.27 meters per second is equal to 0. This guy is 0. Minus 9.8 times delta t. And I can drop these minuses here because minus on the left, minus on the right, minus 1 over minus 1, or minus divided by minus will be plus. But solving for delta t, I'll divide each side by minus 9.8 simply. And they should also be the same unit, but let's drop the units there. I dropped up there. So delta t then, going back to my calculator, should be this number divided by 9.8. As you are working on 4.5 seconds, working on the questions on master, and try to do the same. Try not to round until the end. You still put the answer, first answer as rounded as I did in here, but I'm gonna use the full number to get to that. 4.25 was it? 4.52. All right, rounded version of that would be. Now, does this make sense? Remember, we draw an ugly picture. We say evaluate the problem, understand what is happening, and then think about what equations you can use to solve them. We did that. We solved the problem, and then at the end we assess. 4.5 seconds. Drop from 100 meter. If we drop something from 100 meter, it's not going to take a long time to drop. You can try. It's very hard to, even from 2-3 meters, to set up the timer and stop it. It's really fast. Because the acceleration is 9.8 meters per second squared g. It's a quite large acceleration, so it makes sense to me. This question I'm going to leave to you to work on, but I'll put the annotated version of this so you'll have the answer there. It's a very similar one, except simpler. We have passenger on a giant drop. You know those drops at Six Flags. I hate them. I don't like them. I don't want to do free fall, but some people likes them. So you have a drop. You're dropping here. You're tied to something, probably holding on to it, and you're very scared. Sitting on a chair and dropping down. That's a free fall. I don't know how much fun that is, but I don't want to check. So we have g, downward 9.8 meters per second squared as our acceleration. All right, so right away when I see a giant drop free fall right at Six Flags, I imagine that. Not only imagine, I also draw it to help my imagination and help me solve the question. Sitting cars are raised to the top of the tower. The cars are then released 2 seconds of the free fall. So they are released. Assume this is the top of the tower. There will be y initial. There will be y final. And I don't know the height or delta y. Again, this is often called height. But I know the time. Time it takes to fall down is 2.6 seconds. All right. How fast are the passengers moving at the end of this? Speeding up. Well, of course, they don't fall exactly on the ground, but I draw my line here. The ground is a little bit beneath, right? Otherwise, they would get hurt. And they will have a VY final. Now, that is my question. Do I know VY initial? Yes. If they are dropped in free fall, there is no initial speed. It's 0. Now, what is the minimum possible height of the tower is the second part. So I'm looking for Vy final and delta y, or height of the tower. Similar to delta x, we can always choose one position as 0, the other will be the height. So I can set this to be height, y initial to be height, and when they reach the final point, I can choose this to be 0. Inverse also works, only if you choose the higher point to be 0, you'll find the height to be negative, but it will be correct value. Again, you can take the absolute value. But generally, book goes with this to be initial, higher point to be height, and then the ground or the final reaching point to be 0. So I'll go with that. Then I'll say delta y is equal to y final minus y initial. In this case, it will be minus height, right? So let's look at the absolute values. All right, let's go now find this guy. If I know the time, I'm gonna find Vy final is equal to Vy initial minus g delta t. Vy initial is 0. My Vy final will be negative, so I'm gonna do a trick here. I know this guy should be negative. Well, this is also there. I can just leave it. Minus 9.8 meters per second squared times the time it takes, 2.6 seconds. Again, this minus means it's downward, that's all. So Vy final you will get from there. And then I can go either this way. Vy final squared is equal to Vy initial squared minus 2g delta y. And we decide that this is minus h. Notice how minuses will cancel, which is why we can ignore them. But we should be really careful. Sometimes it may not be a good idea. So let's not ignore them. So what I will have from here, when I replace delta y by that, I will have Vy final squared. Negativity cancels here because I'm taking square. This due to 0, and plus minus minus becomes plus, so I'll have 2gh. And if I have a 0 initial speed, folks, if you are comfortable, put this in your notes. This equation will always hold. Holds if Vy initial is 0. The object could be going upward. You can also use this. Then Vy final will be 0. Oh, let me not tell you that. Okay, sorry, I'm confusing you here. Let's stop here. This holds if Vy initial is 0, an object is going down, the others slightly different, very similar, so let me not confuse you here. I'm gonna solve for h here, the height, and it's equal to Vy final squared over 2 times g. So get this guy, put it here, find the result. Alright, I'm gonna stop here, and again I'm gonna post these as well as annotated. Solve this question and check the answer later on.